Okay, this video is some comments on section 1.3. So we're starting to talk about the components of a mathematical system. This one is sometimes called a logical system so that it's not confused with the other usage of the word or the phrase mathematical system. Sometimes we use mathematical system to mean like a set of numbers or objects or things, like one you've used before is the set of real numbers. Okay, so sometimes a system is a set of things like that and then some operations. So for real numbers we talk about operations of addition and multiplication and so forth. So this is a logical system, and its components are undefined terms and defined terms. So those are phrases or words, whereas axioms or postulates and theorems, those are more statements about the definitions and the terms that were used in undefined and defined terms. Okay, so undefined terms, these are things that we intuitively have an idea of what those mean, but we haven't locked down a formal definition or way of describing those things. And I like this definition for undefined terms. They are things that do not fit into any previously determined set. So this is like a set theory definition, and if you think about other things like maybe a triangle is not an undefined term because it fits into a larger category or set that we've already described. So sometimes we think of a triangle as a shape or a 2D figure or a plane figure, sometimes a polygon, but it's part of a larger category. Undefined terms, that's not the case. So recall that our three undefined terms in this textbook are point, line, and plane. Okay, so if you try to think of a larger category for point, well, intuitively, Euclid would say a point is that which has no part, but there's no larger category like what is a point falls into what collection of things, and there's nothing really that point falls into. Then we move on to definitions, and here are the components of a good definition. First of all, it has to name the term being defined. It places that term into a set or category, so that's what makes it different than an undefined term. And then it has to have enough information to distinguish the defined term from other terms, but we don't want to include unnecessary information. So it needs to be general enough that we can apply it to all of that type of a thing. Like for instance, a definition of a triangle, it has to be general enough to refer to all triangles. We don't want to include unnecessary information about specific types of triangles, but we have to include enough information so that we don't confuse a triangle with a square or a circle or something like that. And then the fourth component, it must be reversible. So your textbook talks about equivalent sets, right? So we have two statements in a definition, and the two statements must refer to equivalent sets, right? So for an example, here's the definition of an isosceles triangle. It is a triangle that has two congruent sides. Okay, so if you think of the set of isosceles triangles and the set of triangles that have two congruent sides, we want those to be the exact same thing for this definition. And that is the case. And another way of saying it is that we could reverse these two statements. So the definition is still correct if I flip this and read this: a triangle that has two congruent sides is an isosceles triangle. All right, for the second statement, two angles are congruent if and only if they have equal measures. This is a definition as well. So I can look at the set of congruent angles and the set of angles with equal measures, and they are one and the same set. So this if and only if captures that reversible aspect of definitions, that you can flip-flop these back and forth. Okay, so you can read this both ways. If two angles are congruent, then they have equal measures, and if they have equal measures, then the two angles are congruent. There is an abbreviation for if and only if. It's this I with two F's, so that's not a typo. That does mean if and only if. And then the symbol for that is this double arrow, and that comes from the formal logic symbol or the use of the arrow So when we looked at the law of detachment, we had if P then Q, and you've seen this single arrow before, or in other words, P implies Q. Okay? And so what we're saying here, if you see the double arrow, it means P implies Q, and also Q implies P. Okay, so that's again, capturing the reversible aspect of a definition. Here's a statement that's not a good definition. So let's say I write a square is a rectangle. Square is a rectangle. Okay, so it's a true statement, but it's not a good definition. And here's why. It does name the term being defined. Okay, it names the square, so that part's okay. It places the term into a set or category. So it's saying that a square is part of the category of rectangles. Okay, so that's good. It distinguishes the defined term from other terms. I don't know that it does that, so we don't have enough info in here. It almost makes you think that all rectangles are squares the way that it's written. Okay, so there's something about squares that makes them specifically a square and not just any of the rectangles in that category. Okay, so I don't know if it fits that part. And then it's definitely not reversible. So if I flip this and say a rectangle is a square, that's not true all the time. The rest of the section deals with some initial postulates and definitions. So here's the first one. Through two distinct points, there is exactly one line. Okay, so this is true in Euclidean geometry, but not necessarily in other types of geometry. There are a few implications here. First of all, one implication. There's a unique line segment determined by two distinct points used as endpoints. So in other words, if I look at points A and B, okay, and if I then refer to line segment AB, there's no confusion as to which segment AB I mean, because there is only one. Okay, because if there were more than one line segment through AB, then that would mean there's more than one line through AB. And we know from this postulate that that's not the case. Okay. The ruler postulate, this is the one that lets us measure line segments and label them with some sort of a length. So the postulate itself guarantees that when you measure the line segment, it gets a unique positive number to describe that measure. But the implications are that there even exists a measure in the first place, and that measure is unique, that there's no other length that could describe that line segment. There is a fun symbol for that. This backwards capital E means there exists. Okay, as in there exists a number measure for each line segment, and then if you follow that by an exclamation mark, that means a unique. So there exists a unique number measure for each line segment. Okay, some other postulates. The segment addition postulate. If X is a point on line segment AB, okay, and then recall that this means that X is between A and B, or in other words, visually on a line segment. Okay, if I call this A and B, then X is somewhere on here. Okay, so I'll put it here, could be anywhere. So if X is a point on the line segment and it's between A and B, then the length AX plus the length XB is equal to the length AB. Okay, so you can add two small portions of a line segment, and that equals the whole. If two lines intersect, they intersect at a point. This is another one that's not true in all types of geometry. Okay, but if you picture two lines intersecting, okay, there's no other way for them to intersect than in a point, and they intersect in exactly one point, not more than one, or anything like that. Through three non-collinear points, meaning not all on the same line, there is exactly one plane. And the fun illustration for this is like the three legs of a stool. And no matter what lengths they are, so here's your stool, okay, no matter how long those legs are, they're always going to be balance the stool, assuming that the floor is flat. Okay, so if the floor is a plane and completely flat, then that stool will always balance perfectly on the floor without wobbling. Okay. Somebody did an illustration of this that I liked in class, and if you hold up 3 pens or pencils, okay, and if you kind of adjust the length so you can move some pens up and down, etc. There's always a way to lay a piece of paper so that it's touching the tops of those 3 writing utensils. All right, if 2 distinct planes intersect, then their intersection is a line. So again, a bit hard to visualize planes, but if you hold up 2 pieces of paper and try to show the intersection, you'll always see a line, a set of points where those intersect. Okay, so maybe picture like the covers of a textbook, and they intersect along the spine. Okay. What about for more than 2 planes, like let's say 3 planes? So you might want to think about if 3 planes intersect, is that all 3 at this touching together? Is that a line, a point, another plane? What would that look like? And then finally, given 2 distinct points in a plane, the line containing these points also lies in the plane. All right, so take a piece of notebook paper, draw 2 points on it, okay, and then if you were to connect those points, we already know that there's, from earlier, there's only exactly 1 line through those 2 points. So if you draw, if you draw the single unique line through those points, you would be drawing it on the piece of paper. Okay, there's no way for that line to not be in the plane. Now that's not true necessarily in other types of geometry, like where space is curved. So picture, just as an example, let's say you curve your piece of paper up. Okay, then you'd be able to maybe punch holes through the paper where those 2 points were, and then there would be a way that you could see that you could get a line through those points that's not necessarily flat on the paper. All right, there are some definitions in this section, so I didn't write all of these out. I figure you can read through the section on your own and look at those. But the 2 I wanted to talk about were union and intersection, and these are set theory types of concepts or phrases here. So the union symbol is just an upside down capital U. It looks like that. Okay, an intersection is, right side up U. Intersection is the upside down U. And a union informally talks about joining or combining 2 different things. If we looked at sets, like set C and set D, the union of sets C and D is everything that's everything in C, in set C, or set D, and then that's implied, or both. Okay, so things in both C and D are part of that union. Okay, so you're joining 2 things together. And in geometry, a lot of times the things you're joining are either figures or sets of points. All right, so array is defined using this word union. Okay, so if we talk about ray AB, and here's the symbol for it, you draw a little arrow, a one-sided arrow over AB, and that's the union of segment in AB and all points on, and this is a typo, this should be line AB. Okay, all points X on line AB, such that B is between A and X. All right, so let's try to draw and visualize this. Okay, so we have the union of segment AB, okay, and then if I were to extend that and look at line AB, okay, then my ray includes not only this segment, but also any point on the line so that B is between A and X. Okay, so B is between A and X, so that would be all of the points X, kind of on the opposite side of B than A, so all the points over here. And you would just keep on going. Any point that meets that, that criterion is over here, so okay, all of those, and you end up just with this infinite arrow sort of extending to the right. Okay, so that's array. And then the definition you may be more familiar with is It's the geometric figure that starts at A and then goes past B and continues forever in that direction. Sometimes we call rays half lines for that reason. Okay. Now, if you wanted to indicate the ray that starts at B and then goes past A, okay, that would be BA, but you would still draw the arrow the same way. Okay, so if you're going the opposite direction, you switch the order of the letters, but the arrow usually points to the right. All right, and then intersection. So union is joining or combining together different things. Intersection is what two sets have in common. Okay, sort of like the overlap of two things. All right, so we talked about two planes. If they intersect, then the part that they share in common is a line. So that's an example. We also talked about if two lines intersect, then their intersection is a point. So this one's a little easier to draw. Okay, so if I draw two lines intersecting, then the only part that they have in common is this intersection point. Okay, so that was section 1.3, and then some comments on section 1.4, angles and their relationships. Okay, here it is again using the word union in a definition. An angle is the union of two rays that share a common endpoint. So there are a couple components to an angle. It's got two sides and a vertex. So you've got, here's ray number 1, and then here's ray number 2 that shares this common endpoint, and together those make up the angle. So notice that the angle, it's not actually the space in here, okay? It's not the space between the two rays. So like a piece of pizza is not a good illustration for an angle because an angle is not a space, it's just sort of the edges of that space. All right. The protractor postulate is sort of similar to the ruler postulate, just for angles. So this one allows us to measure angles and assign them a unique positive number. Okay, so we usually do this in degrees. There are other ways to measure angles, like radians. Okay, but no matter what unit you use, there's a unique positive number that gets assigned to the measure of the angle. Okay, and we're assigning that measure based on kind of like how far apart those two sides of the angle are. The angle addition postulate says that if a point D lies in the interior of an angle, which we do need to define, the interior of an angle ABC, then measure of angle ABD plus DBC is the measure of ABC. Okay, so let me draw this one. All right, so let's look at angle ABC. All right, so the way that this is named, B must be the vertex, and A and C must be on the sides. And then D, intuitively, the interior is just kind of in the middle of the angle, so we'll throw it in here somewhere. Not exactly halfway in the middle, just somewhere inside that sort of space. All right, and then if I was to, let's put a line or a ray through that point, and that's D. Okay, so the measure of angle ABD, this one, plus DBC, these two little pieces together makes up the measure of angle ABC. All right, so let's talk about a definition for the interior of an angle, and I did post something on our website with the more formal definition, but if it's sort of bothering you to just intuitively describe the interior, then maybe this would help. All right, so here's our angle, and let me do a color that shows up better. And I'm just going to extend and draw the angle with lines as sides. Okay, so here's A, here's B, here's C. Okay, and to go with this definition, we also sort of need to have an intuitive understanding of the fact that there are two sides to a line, right? So if you think about a line, it cuts a plane in half, and a point can either be on this side or this side of the line, or on the line itself. Okay, so those are the three options. But we sort of know intuitively what's meant by like the side of a line. All right, so back to the definition of the interior of an angle. We say that it is the intersection of points on the same side, of line AB, as point C. Okay, it's the intersection of that with the set of points on the same side of line BC as point A. Okay, and that's the definition for the interior of this angle. All right, so let me shade this to show you this. So the points on the same side of AB as point C, that would be all of these points. All right, and then points on the same side of BC as A would be these points. Right? And then you can see where the shading overlaps. It's in here, and it would sort of continue out. Okay? And that's what we mean by the interior of the angle. Okay? Now notice the sides and the vertex of the angle are not included because those points aren't considered to be on, like the shading in red here. Okay? The points on AB itself, okay, these are not shaded red because they're not on the same side of the line, they're actually on the line itself. Okay, so the interior is points between the sides, sort of right up next to, but not actually touching the sides of the angle itself. All right, so that's what we mean by the interior of an angle. And then this is talked about in your textbook. An angle divides a plane into three different sets of points. So you have the set of points, we'll call it P, and P is points on the angle. Okay, and then Q is the set of points in the interior of the angle. Interior of angle. And R is the set of points in the exterior of the angle. Okay. And let's say that plane S contains this angle that we're talking about, right? So then P, Q, and R, these three different sets, they describe that plane S if you take all three of those sets together. All right, so we would say that the union of P and Q and R is the same as that plane S. All right, so it's just all of the points in that plane fall into one of those three different sets, P, Q, or R. Okay, and then there are many other definitions in this section. So we have some that describe just a single angle on its own. Okay, so an angle can be one of these different things. It can be acute, right, obtuse, straight, or reflex, and all of these refer to its the measure of its interior in degrees, or whatever unit you're using. All right, so acute angles, and again, remember we're talking about positive numbers, a unique positive number. Right, so we don't really talk about 0-degree angles or angles less than 0 degrees. Okay, so acute angles are ones whose measure is less than 90, and I don't need to specify greater than 0 because that's already implied in the definition of the measure of an angle. Right angles have measures equal to 90. Obtuse have ones that are greater than 90 and less than 180. Okay, straight angles have measures equal to 180, and then reflex are the ones that are greater than 180 degrees. All right, so those are the weird sort of backwards ones. They're kind of like reflexing or bending back on themselves. All right, so we just wanted to sort of talk about the space, like if you have an angle here that measures, say, 80 degrees, okay, then there's another measure out here, and this is a circle, should add up to 360. Okay, so this measure is 280, so we could sort of describe this angle as a reflex angle if we're referring to that space. Then we have some other definitions, and apart from this bisector one thrown in the middle, all of the rest of these refer to pairs of angles. Okay, pairs of angles, or sometimes multiple angles, but usually we talk about them in pairs. Okay, so adjacent angles are ones that are next to each other, and also they must share a common vertex. Okay, so for example, this angle and this angle are not adjacent. They are sharing a side, but not a complete side, and their vertices are two different ones. Okay, so those are not adjacent. Congruent angles are ones that have the same measure. Some congruent angles are also adjacent, and some adjacent ones are congruent, but it doesn't necessarily have to be both of those two things. So you can have congruent angles that are not next to each other. Complementary, their degrees add up to 90, so their sum is 90 degrees. And supplementary are two angles which add up to 180 degrees. And then vertical angles are formed when you have two lines that intersect, okay, and then the angles opposite from each other are vertical. And we also know a fact about vertical angles, and intuitively you can see that they're the same measure. So all vertical angles are also congruent. Okay? And then a bisector is anything that divides something in half. We can have a segment bisector or an angle bisector. Okay, so for a segment, this is segment AB. We didn't define this yet, but we'll get to it soon. The midpoint is just the point at the exact middle of the line. Right, so a bisector would be either a line or a line segment or array that goes through that point. Okay, so this could be, all right, this segment could be a bisector. I could put this line through the middle, and as long as these two halves of the line segment AB are the same, okay, and as long as these bisectors pass through the midpoint, that's what makes them a segment bisector. And then angle bisectors divide an angle into two congruent smaller angles. Okay, so here's an angle, and we'll call it ABC again. So the bisector of an angle, it's got to pass through B and be in the interior of the angle. Okay. A segment wouldn't work, okay, because if it stops, then it doesn't keep on, like our angle keeps on forever. So we need to continue the bisector forever as well to keep on dividing that angle. Okay, and it's dividing the interior into two spaces that are the same size in terms of degree. Okay, so like this could be like 40 and 40, for example. All right, and then you name a bisector. We would need at least one other point, so maybe if I put like point D on here, then I could say that, in this case I've just drawn a ray, so ray BD is the bisector, or the angle bisector, of angle ABC. Okay, and then there are some examples in the textbook. I won't go through all of these. You can read through the steps yourself, but these deal with algebraic problems based on these angle relationships. Okay. The setup for number 5 is interesting. So notice, I just want to point out, if you're solving for x and y, then if we're trying to use equations, we have two variables, so you're going to need two equations. Right? So be thinking about the relationships. We're given some expressions for 5, 8, and 6. Okay, we know measure of angle 5 is 2x plus 2y. Measure of angle 8 is 2x minus y, and then 6 is 4x minus 2y. Okay, so I won't say anything more about that, but refer to that one in the textbook to see the steps to solve for x and y. Okay, those are all the comments I have for these two sections.